All right, so what we're going to talk about now is the possibility that when we put together the cross-section of a member that is going to be loaded flexurally, and remember, we call those kinds of members beams, right, if we're planning on loading it in flexure, we are looking at a case where, let's say you have dissimilar materials that you are bonding together in some way to make a composite shape of the ultimate cross-section that is going to form the beam. Okay, so this is a little different. You've already seen in the past that you can find second moments of area for cross sections of beams if they are made, we call them like composite cross sections, meaning that they have several different kinds of shapes that are all put together. But one form of composite cross section we have not talked about in any of your classes yet is if you use dissimilar materials, because every material has a different elastic modulus. Probably, right? If it's a different kind of material, you can't expect it's going to have the same elastic modulus as something else. And so what I want to do is show you a technique that we can do if you make beams in this way where you use multiple different kinds of material. Okay? Actually, this is a pretty efficient way to make certain kinds of beams. And a good example that I can kind of point out right here is some of you may have seen what's sometimes referred to as foam board or foam core. And essentially what they do with that kind of material is they take a very light, because it's not very dense, it's got maybe a lot of air in it, like foam core, and then they glue paper layers to the top and bottom of that foam core. What they're doing in that kind of a case is they are taking this very light foam that isn't very capable by itself of resisting flexure, and they're using that more or less as kind of a spacer, right? So that they're spacing apart two layers that are better at carrying flexure, right? Making them further apart away from each other. And if you remember like what goes into a larger I value, second moment of area value in MC over I, one of the things that matters a lot is how far away from the neutral axis are the fibers that are carrying the stress. So essentially a way of building a beam like this, the main point of the foam is to separate the fibers that are actually carrying the stress and getting them further apart from each other, right? But in these kind of cases, it's not that the foam is not contributing anything, right? The foam is contributing something, and so there's a little bit of a technique we can use to kind of figure out what the overall sort of resistance to flexure is going to be of one of these composite members like this. Is that fair? Okay, so what I want to look at here is sort of maybe the most simple case, and we'll get started there. What if we have a beam that is loaded with two different, or it's constructed with two different kinds of material, right? Material 1 on the top, material 2 on the bottom, okay? And just for the purpose of like being clear for my sort of description of things, let's assume that in this example, E1 is greater than E2, meaning that this top layer of material right here is stiffer than the bottom layer of material, right? Okay, so if we then take this profile of beam and subject it to a bending moment, right? What you'll see happen, like with any bending moment, is you might take that beam and it might transform into kind of a smiley shape like I'm showing right here, okay? If that's the smiley shape that it transforms into as a result of loading it with this bending moment of M, then what does that mean as far as how much the top part of this beam changes in length? Is it increasing in length or is it decreasing in length on the top strand of this beam? Decreasing. Yeah, that top strand is decreasing because it's kind of more to the inside of this circle or this portion of a circle that we're creating, right? The bottom strand, on the other hand, does what? It gets longer in length, right? So we can sort of infer from this that there must be some kind of a compressive strain that is happening on the top strand of the beam, whereas there's a tensile strain that is happening along the bottom strand of the beam, okay? Now I won't recover it right now, but in the coverage that we've had of MC over I, we've seen that there's actually a linear distribution of strain that goes across the face of this material. In other words, it's kind of a straight line distribution such that, let me kind of sketch this for you for this example right here, such that we might have a certain amount of strain. Here we're saying E1 is greater than E2, so that tells me that I would actually kind of expect that the neutral axis where there is zero strain, where would I kind of expect that to be? That'll help me sketch my strain profile right here. Okay, let's kind of take it to the extreme. What if material 1 is steel and material 2 is Play-Doh? Okay, what does that essentially do? That'd create a neutral axis that would be pretty close to being right in the middle of material 1, right? So what we see there is that by E1 being greater than E2, it's going to have the effect of shifting the neutral axis upward probably. Does that make sense? So that's where I'm going to show it to have a somewhat realistic description of how this is going, right? So let's say my neutral axis is now occurring maybe somewhere like right there. Okay, or I mean, it doesn't necessarily matter exactly where I put it, but you know, it's probably going to be shifted upward somewhat relative to the actual middle of the cross section. Okay, and we said a second ago we're going to have compressive strain that is happening in the top strand of this material. So what I'm going to do is show a linear profile here for strain, such that it starts right here, right, goes through my neutral axis point and comes down here, and you can see there that essentially the way that that strain is going to now be distributed is that we're going to have some compressive strain up here, but then when we come down here we have all this tensile strain that comes back this way. Okay, and I guess the big point I want to make here is that the fact that we have dissimilar materials, because they are bonded firmly together, it doesn't have any effect on the profile of the strain that happens here, because the profile of the strain is happening by virtue of the fact that it's essentially the shape of this curvature of this beam is what creates this strain profile. Okay? So, as long as we're okay with that, we can now move to the next step and say, let's go ahead and apply the assumption here that in the process of straining this beam, we have not gone outside of the elastic limits of either of my two materials. Okay? And if I haven't gone outside the elastic limit of either of my two materials, that means that they are still both behaving elastically, right? And if they're behaving elastically, then there's probably a relationship between stress and strain, right? What is that? Do you remember what that relationship is? Okay, I'll put here in elastic region. The relationship between stress and strain goes like this. Stress is equal to elastic modulus times strain. So now my next question is, which elastic modulus? We have two of them playing in this situation, right? We have two different materials that are a part of this beam. So my question is, which elastic modulus? Or do we use both of them? Okay? And the answer is we probably want to use both of these elastic moduli, right? And we'll do it like this, such that we'll notice that because we have compressive strain above this point where we have our neutral axis, right? I'm going to represent that with this, line coming up like this and showing this is going to have compressive stress happening on that surface because I have that compressive strain on that top part, right? And then when it comes back this way, at the same slope where it came in right here, I'm going to start having tensile stress, right? And again, that's going to be tensile stress coming that way because I have tensile strain below the neutral axis point, okay? And if I want to try to evaluate, kind of what these slopes are, essentially I can just transform what these strains were by multiplying by the elastic modulus and I get the stresses. But what happens here is now I transition from being E1 to E2 at this point, right? And because I'm transitioning, what does that do instantaneously right here to my amount of stress right as I go across this profile change, this material change in the profile?
Changes the slope?
Yeah, well, it changes two things. It does change the slope, but it also changes the value, right? So both of those change such that if I plot what this stress looks like from here on, it might look something like this because material 2 has a lower elastic modulus. So essentially the slope has changed, but also the value itself changed instantaneously right there at the transition point between the materials. Okay? But these will continue to be tensile down here. Okay? Now, here's what's tricky. because I have changed up the way this stress profile looks, my assumptions that I made when I derived my fancy equation of MC over I or My over I, my flexure stress equation, this messes up my assumptions I had built into that equation. Because one of the things I assumed in that equation is that there would be a uniform distribution of stress, right, linearly distributed across the whole face. Now I have an interruption in that perfectly linear distribution across the face, right? Oh my. So what do we do about this? Okay, well, here's the good news. We do have something that we can do about it, and this is one of the most common techniques that's out there to be able to deal with this. In order to restore this back to a kind of consistent stress profile so that it's linearly distributed across the entire face, what we can do is we can pretend like we have a different amount of area of the material. And that will have essentially the identical effect as decreasing the amount of stiffness. So if I can basically get the same effect mathematically by reducing the area as opposed to reducing the E value. And if I do that, and if I get that area reduced to the right amount, I can treat the whole cross-section as if it is the same E value. And then I'm back to being, for that transformed area, I'll be back to being a linearly distributed stress again, which is what I want. So the question is, what do I need to do to basically reduce this down? And the answer is actually pretty simple. We're going to define this thing called a transformation factor. Okay? We'll use the letter N. That's what our textbook uses for it. N is going to be equal to the elastic modulus of the material that we would like to transform, right, which in our problem right here is E2, divided by the elastic modulus of the material we are transforming into, which should match the one that we're not changing. Does that make sense? So I take the ratio of those two E values. That essentially is going to become a factor that I can multiply by the original width of the piece that I am trying to transform to get the new width of the piece that I'm trying to transform. So essentially what I'm saying here is that if my original width of my part right here was W, right, which I guess I already had that on the picture, but I wrote it again. If that original width was W, this new width that I'm going to have right here, that new width is just going to be equal to this transformation factor times the original width. And the reason for this is that these relationships are all linear, so I can just apply it like this, and instead of imagining that I have a rectangular cross-section now, I now treat it as though I've got kind of this T-shaped cross-section where the entire cross-section has the same elastic modulus E1. Okay? And as far as finding things like the stress in the top part of this beam, it'll work exactly the same way. Okay? And I'm being careful about how I say that. The stress in the top part of this beam that originally was E1, the stresses I find now treating this cross-section that is changed like this will be correct. If I want to find stresses, though, in the bottom part of the beam, I'm actually close, but what I need to do is multiply whatever results I get for my stresses in the bottom part of this beam. I need to multiply it again by my transformation factor to get what the actual stresses were in the bottom part of the beam as opposed to these transformed stresses that I have pretending like this material is like E1 value instead of E2. Okay, so to try to make that make a little bit more sense, right, essentially I've got that summarized right here, that to get whatever your actual stress is in your transformed portion of the beam, you just take your transformation factor and multiply it by whatever your transformed stress would turn out to be. Okay, so to make this make more sense, let's do a quick example. Okay, and here's the example that we're going to work right here. It says, find the maximum stress in the steel and the maximum stress in the aluminum for this cross-section. Here's how the cross-section is constructed. I have a circular part that is steel on the top part of this beam. It has a radius of 50 millimeters. Okay? It has an E value of 200 GPa. Okay? Then I have a rectangular little tail kind of thing on the cross-section of the beam that sticks down. It has an E value of 73.1 GPa because it's made of aluminum. It has a height of 150 millimeters and a width of 15 millimeters. okay? What I'm showing here from the other side is essentially a side view of what this cross-section of the beam is, and I'm showing that it is having to carry a bending moment of 45 kilonewton meters, right? So we're supposed to, with that information, figure out what my maximum stress is in the steel and what the maximum stress is in the aluminum, okay? And where I'm going to start with this process is decide on which portion of the cross-section I would like to transform, okay? And in this case, because I have this rectangular piece down here, rectangular pieces are especially easy for me to figure out, you know, how to transform them in terms of width to make this work. So I really like the idea of transforming the bottom piece as opposed to the top piece, okay? So what is my transformation factor then? Okay, what it's going to be is I need to take the ratio of whatever my elastic modulus was of the bottom piece, the tail, that's the one I'm transforming, right? So that was 73.1 GPa, right? And I'm going to take that and divide it by the elastic modulus of the top piece, right? So it's going to be 200 GPa. Okay? And out of this, I can calculate what this transformation factor, I have that it turns out to be about 0.3655. Okay? Now with that transformation factor, what I'm going to do is go into this cross-section, and instead of imagining whatever the original width was here, right? The original width, I'll do it in gray just like the other piece, the original width was 15 millimeters, right? Okay? What should the new width be now? In the transformed state. It's going to narrow up a little bit because I'm going to pretend like it has an elastic modulus of 200 GPa, right? And I'm just going to kind of make it still equivalent by changing the width proportionally. So if I'm pretending like it's stiffer, then I need to pretend like it's narrower in order to get the same effect as far as the stress distribution. Does that make sense? Okay? So what I'm going to do there is show that width, and I can calculate what it's going to be based on taking my transformation factor, right, of 0.3655 and multiplying that by the original width of 15 millimeters. And that's kind of, I guess, the first little, it's not really that tricky, but that's kind of the first little trick, is to go ahead and get the section transformed into the shape that we'd like it for it to be. And from that point forward, we work the problem as though this is actually the shape. Okay? Yes?
Does the height change?
The height is not changing. We are only changing the width. And here's the reason for that. Okay? If you imagine what the I value would be for a shape like this, okay? The I value is going to be calculated with the base times the height cubed divided by 12, right? So if you don't remember those perfectly, it's okay. You'll have that as reference information on your tests and whatnot. But that is one that you should be learning, you know, somewhere along the way, is that your I value for a rectangle is BH cubed over 12, right? So if we transform the height, that is actually not going to have a linear effect on this section's ability to react against moments, right? Whereas the width, because the width is the B in the BH cubed over 12, that is going to have a linear effect. By changing that width, it'll have a linear effect on its ability to resist the flexure. Does that make sense? Okay, so that's how we'll transform that width. The height stays the same, so I'm going to put that in here as 150 millimeters. And I think everything else we still have here. If we were trying to solve this problem, right, where we've now transformed one of those dimensions here a little bit, the first thing that we would need to do is find a centroid so that I know where my neutral axis is going to be for this cross-section. That makes sense? So what do I do to find the centroid? What you're going to start with when you do a centroid is say, what am I using as my reference axis? Okay? And for this one, let me just call this down here the reference axis. When you say reference axis, what are we talking about? Yeah, for us to know where the, he said the origin basically, right? For us to know where the centroid occurs, we have to know relative to where, right? So I'm going to call that the reference axis, meaning that what I'm trying to calculate here is essentially what is this height, y sub c, right, up to that point that is the centroid. Okay? Now what would this calculation look like? Do you remember these? The calculation is essentially the sum of the area, the sum of the product of each area of each of the pieces of the section, right? I've got all the different sort of primitive shapes, circles, rectangles, triangles, that kind of thing. So I need to take the centroid of each of those composite shapes, right? A circle, in this case, a circle and a rectangle. How far those are from the reference axis multiplied by the area of each of the pieces, add all those up, and then take that and divide it by the total amount of area. So essentially what that would become here is this. I'm going to start with the circle up here on the top. What is the y centroid relative to the reference axis to the centroid of the circle? Should be 150 millimeters plus what? Yeah, since 50 is the radius, it'll just be 150 millimeters plus 50 millimeters, and that'll end up giving me 200 millimeters. Okay? And that's what I was talking about a second ago as far as the location of the centroid of that shape. Now I need to multiply that by what? The area of the shape, which I can do with pi times r squared. Okay? And to this, I'm going to add, that's the contribution, by the way, of the circle that's up there on the top. Now I'm going to add the contribution of the rectangle that's down here at the bottom. So I need to know what's the location of the centroid of the rectangle. Right, half of 150 millimeters, which is going to be 75 millimeters. That's the location of the centroid of that piece, multiplied by the area of the piece, and this has to be in its transformed state, right? So what that means is that the area of this piece is going to be equal to the height of 150 millimeters, okay, multiplied by 15 millimeters. Okay, let me give myself just a smidge more room here. Multiply this by 15 millimeters, multiplied by 0.3655. I'll just call it good. Okay? And I divide all this by what? Okay, the sum of the areas, which is just going to be equal to pi times 50 millimeters squared plus 150 millimeters times 15 millimeters times 0.3655. Which, by the way, I could go in here and say that product right there winds up being 5.4825 millimeters. Okay? Now with all of those values plugged in, I can calculate what y sub c is. Y sub c winds up being 188.15 millimeters. Okay, you're talking about, what's your question? I'm talking about the bottom part of the equation. Yeah, so this is the sum of the areas of each of the shapes that make up the total shape. Okay, so it'll basically be the area of the circle plus the area of the rectangle. Okay, so now I know where the centroid is. That's important for finding my second moment of area because I essentially need to not only deal with the individual second moments of area of each of the shapes, I also need to apply parallel axis theorem, and for that I need to know what the distance is from the neutral axis of the whole composite shape relative to each of the component shapes. Okay, and so here's what that might look like, right? For my I about the neutral axis passes through the centroid of the cross section, right? Okay. What I need to do is first figure out what would the second moment of area be. I'll again start with the circle up here. What would the second moment of area be for the circle around its own centroidal axis for the circle? And that is something you may or may not remember, but the formula for it is going to be 1/4 pi times the radius, and the radius here is 50 millimeters, and that's to the 4th power. Okay, so far this first term that I've put in my I about NA calculation is just the second moment of area for this first shape, right, around its own centroidal axis. To this I need to add what to get its overall contribution? Distance from the neutral axis. Here's the easiest way to do that. I know that from the bottom of this shape to the neutral axis is this y sub c value, right? I also know that from the bottom of the shape to the middle of the circle is going to be 150 millimeters plus 50 millimeters. So if I take the difference between those two values, it gives me how far it is from the neutral axis of the shape to the middle of the circle. Does that make sense? So that's really what I'm trying to hit, is essentially I'm trying to get this distance from the neutral axis up to the middle of the circle. And to get that, I can take 150 millimeters plus 50 millimeters minus y sub c. Fair? Okay? So I'll do that, get 200 millimeters as the sum of 50 millimeters plus 150 millimeters minus y sub c that I just found up there. I'll go ahead and do that substitution as well. 188.15 millimeters. And that needs to be squared for parallel axis theorem purposes, right? Parallel axis theorem says you take the distance squared between your neutral axis of the whole shape and the centroidal axis of the piece that you're trying to evaluate and multiply that by what? The area of the shape itself. And so that, we already did that earlier too, right? Pi times 50 millimeters squared. So now, these first two terms that I have written for I about NA, that is essentially the contribution of the circle shape to the overall second moment of area of this cross section, okay? What else do I need to add? Contribution of the rectangle, and so for that I need to know what is the second moment of area of the rectangle about its own centroidal axis, right? How do you calculate that? Base, right? That base, I now have written it this way, so I'll go ahead and use that, right? 5.4825 millimeters base times the height cubed, right? 150 millimeters cubed over 12. So that's the second moment of area for the rectangle around its own centroidal axis. To this, I need to add the distance from the neutral axis of the whole shape to the centroidal axis, right? That's this distance right here, the centroidal axis of the rectangle, okay? And so to get that one, what do I need to do? Y sub c, 188.15 millimeters, minus what? Half of 150, right, which is 75 millimeters, like this. That gets squared. And what do I need to multiply that by? The area of that rectangle, right? So the area of that rectangle is going to be 150 millimeters multiplied by this transformed width of 5.4825 millimeters. And that should be it now, because I've evaluated essentially the contribution of both the circle and the rectangle. I get that this overall value comes to 18.082 times 10 to the 6th millimeters to the 4th. Okay? Yes, ma'am.
So we add the contributions from the circle and the...
Yes, I didn't put the plus over there, but yes, we're going to add that contribution as well. Okay? The only time you subtract contributions is if you actually count area in the process of like adding and subtracting areas. Like sometimes you count area that's not really there, so you have to subtract it back off. We didn't have that in this case, so we're not subtracting any contributions in this case. Okay. Now, we have everything that we need to find the bending stress for the steel part, right? All we use is just MC over I, okay? So stress equals MC over I, okay? What's my M value? Okay, up here it says 45 kilonewton meters. Let me do something real quick here. I'm going to transform my 45 kilonewton meters. Let me do this kind of once and for all up here. 45 kilonewton meters. If I want to transform this into Newton millimeters, how do I do that? Okay, are there 1,000 newtons per kilonewton? You agree with that? And then there's also 1,000 millimeters in 1 meter, correct? So this basically says this is 45 times 10 to the 6th Newton millimeters. I'm going to show you here in just a second why I wanted to do that real quick. Okay? So let me put that in here as 45. Give me a little more room here. 45 times 10 to the 6th Newton millimeters. Do you remember what C was in MC over I? Right, it's a distance from the neutral axis, and it is either measured to the very top fibers of the beam or to the very bottom fibers of the beam. If you want the overall maximum stress, you pick whichever of those is larger, okay? Or sometimes, like in this case, we're not asked for what's the overall maximum, we're asked for what's specifically the maximum in the part that's actually steel, which is the circular part up on the top, right? So what we want to do is not pick any old C, we want to pick the C value that would go to the top because that's where our steel is, right? And so I'm going to plug that in here. What is that value, by the way? Yeah, what you're going to have here is you'll actually have 150 millimeters to the bottom of the circle plus another 100 millimeters to the top of the circle from the bottom over the overall thing. So that's a total of 250 millimeters, right? Then what, though? Right, you got to subtract back off y sub c because that's how far it is from the neutral axis to the top, right? So that's what I'm going to put in here. I'll say 250 millimeters minus 188.15 millimeters. Okay, and then my I value I just calculated a second ago. It is 18.082 times 10 to the 6th millimeters to the 4th. Okay? What can I do with my 10 to the 6ths? Those divide out, right? Now what else with my other units? Okay, in the numerator up here, I'll end up with Newton millimeters squared, right? In the denominator, I have millimeters to the 4th, which what am I left with? Newtons per square millimeter. Do y'all know what a Newton per square millimeter is? Okay. Yeah, that's one that is a good one to know, is that a Newton per square millimeter is a megapascal, okay? And I won't prove it to you right now, but since this is Newtons per square millimeter, this is going to be equal to whatever this number is that you calculate here, but in megapascal. So that'll end up being 153, I have 153.92 MPa. Okay? So here's my question now that I've gotten to the end for finding the bending stress for steel. Did we transform that material in our transformation process? Okay? That means that this stress value does not have to be transformed because we did not transform the steel in our first process. This is the true amount of stress that really is in the steel part. Okay? So there's nothing else to be done on that. This really is the value that we should find. Okay? Now let's think about one other thing here real quick as well. I didn't really care, I wasn't careful with my signs here just now either. Let's go back up and look at our direction of our moment. If I am putting a bending moment, the direction that I'm showing in my original part of the problem, is that creating compressive stress or tensile stress in the top strands of this beam? Compressive, right? So, this is certainly one way to do that, just how I showed you just now. You can kind of do a post check and say, the direction I've got flexure, is that creating a compression action in the top part of this beam or a tensile action? And if it is, if in just your plain evaluation of it without really thinking about sign didn't give you the right sign, you can just go back in and say, well, really, this should have been minus MC over I, and this should be a minus 153.92 MPa. Okay. The other reason that this is true is that technically the formula that we're using here is minus my over I. Okay. And we're plugging in a value for y that is the distance from the neutral axis to the top fibers of the beam, right? So you might remember that version of the equation as well. But anyway, so point is, this is a compressive stress that's happening in the top part of the beam. All right, what about for aluminum? Okay, answer is we do basically the same thing, right? We say that stress is going to be equal to the moment, which is again 45 times 10 to the 6th Newton millimeters. We're going to change the C value here because if we're trying to find the stress in the aluminum, we want to not take the C value from the neutral axis to the top. We want to take it from the neutral axis to the bottom, which is just going to be our Y sub C value, right? That's how far it is from the neutral axis to the bottom of the cross section. So we'll put that in here as 188.15 millimeters. and we will divide this by the I value, which is 18.082 times 10 to the 6th millimeters to the 4th. Now here's my little warning. What we have just calculated here is the stress that we would have at the bottom tip of this beam if it really was all made out of steel and if it really was the shape that we transformed it to. Okay? Problem is, that isn't what kind of stress we are going to see in the aluminum because we have a situation like this happening. Right? It will actually have a smaller amount of stress, and what we just figured out was essentially the stress it would have if that transformation from strain to stress was the same all the way across the whole cross-section. And it's not once we account for the fact that this is actually made out of aluminum. So what do? Good news is all we have to do is apply our transformation factor again, just append it onto this thing, just multiply it. Okay? So we'll multiply it by this transformation factor that was 0.3655. Like this, and this will end up giving us a stress value of 171.14 megapascals. Okay? Any questions about that? What if you had one that was a larger stack? Let's say you had 3 materials stacked together as opposed to 2 materials stacked together. What would you do? Yeah, you might have to have 2 transformation factors. If you have 3 different kinds of material, you might have to have 2 transformation factors, one to transform one of your materials and the other one to transform the other material so that you're making it to where it's all as if it's the same material. Does that make sense? Or if you have a stack of 3 materials where 2 of them are the same, it might make sense to transform the one that's not the same to the ones that are already the same. That kind of makes sense? All right. Any questions? All right.